This is a screencast for section 10.2, example 9, finding the path of the particle. So in example 9, we're going to determine the path the particle in example 8 travels going from 1, 5 to 9, 21. Well, if we look back at example 8, we found the displacement between the points 1, 5 and 921 and then the distance traveled. We didn't actually find the path. I just drew this and totally made it up just for an example. So now we're going to actually find the graph of the path. So the path is r of t, which is the vector with the antiderivative of the horizontal parameter for velocity, comma the antiderivative of the vertical parameter for velocity, finding us the horizontal position and vertical position. I'm going to do those separate. So dx dt is v1 v of t. So that means I'm going to multiply both sides by dt and find the antiderivative of both sides, which then would give me the antiderivative of dx equals, so I plugged in v1. So from example 8, the velocity, the horizontal expression for velocity was t minus 3 pi cosine of pi t. And then of course the dt. So now x of t equals the antiderivative, and then don't forget your plus c. We have a constant here, and the initial value was 0, 1. So at t equals 0, the horizontal position was 1. So I plugged in 0 and 1, 0 for t, 1 for x, and solve, and I get c equals 1. Now the vertical parameter for position, it's going to be found by taking the antiderivative of v2, and then so I plugged in v2 from, again, example 8, 2t minus pi sine of pi t, and I get that y of t equals t squared plus cosine of pi t plus c. Well, at t equals 0, the vertical velocity, vertical position was 5, so I plugged in 0 for t, 5 for y, and I get that c equals 4. So now I can tell you that the path is going to be the horizontal parameter for position plus the constant we found, 1, and then the vertical is going to be the vertical expression for position plus the constant 4. Now I can put that in the calculator. I put the horizontal into x1, the vertical into y1. I found a good t-min, t-max, 0 to 4, because that's what I'm looking for. T equals 0 to 4. Remember, example 8 told us that 1, 5 was at t equals 0, and then 9, 21 was at t equals 4. Then I found a good x-min, x-max, y-min, y-max, and I can see this whole particle's path. And of course, if you graph it on your calculator, you'd be able to see the path as it's drawn. The now try problem actually asks us to do number 37 and 41. So let's start with number 37. That just makes sense. The velocity v of t of a particle moving in the plane is given, along with the position of the particle at time t equals 0. Find the position of the particle at time t equals 3, and b, the distance the particle travels from t equals 0 to t equals 3. So part A, the position of the particle. Well, we don't need to know anything about the path in between t equals 0 and t equals 3. I just need to know horizontally how far did it move and vertically how far did it move to get us to jump from t equals 0 to t equals 3. So that will be displacement. Now, so the position at the end of this t equals 3 is going to be the displacement plus the original starting point. So at t equals 0, which they gave us is 2, 6. So I'm going to put in my vector, the antiderivative from 0 to 3 of the velocity, and then plus the original horizontal position of 2. Then the antiderivative from 0 to 3 of the vertical expression for velocity plus the original vertical position, 6. Take the antiderivative, still need to add 2. Take the antiderivative of the vertical, still need to add 6. Evaluate, and I get 18 plus 2 and then 3 plus 6. So in other words, my displacement was 18 horizontally and 3 vertically, which means the particle would be at a final position of 20, 9. Part B, the distance the particle travels from t equals 0 to t equals 3 is going to be found by arc length. So So that's going to be the antiderivative from 0 to 3, all these little teeny tiny pieces of path that we're going to estimate them by making them straight, will be the square root of the horizontal plus the vertical squared. And that's going to be about 19.34 units. So to get from t equals the point at t equals 0, so 2 comma 6 to 20 comma 9, it didn't go a straight 18 horizontally and 3 vertically. It went 19.343 units somehow. We don't know what that curve is yet. That's what number 41 is asking us. Sketch the path that the particle travels in exercise 37. So to find that path, first we have to find the expression for path. So we're going to take the antiderivative of the horizontal velocity. And of course, to solve for that constant, I'm going to plug in the initial, well, t equals 0, and then the initial horizontal position. And I get c equals 2. Now vertically, I'm going to take the antiderivative of the vertical velocity and again solve for c by plugging in when t equals 0, the vertical position is 6. And that means my final position vector is going to be t cubed minus 2t squared plus 2, comma t plus 1 over pi sine of pi t plus 6. So to graph that, well, to set up my window, first of all, I put obviously in y1 and y2 the horizontal and vertical parameters for position. But the window, my tmin was 0, my tmax was 3. Then I looked at, I actually know where this particle is going to end up at 20 comma 9. So I just adjusted accordingly my window. I did 0 to 23. It started out at 2 comma 6. Let's back up. Horizontally, it started at 2, ended at 20. So I made my x min 0, my x max 23. Vertically, it started at 6, ended at 9. So I started at 5 for my y min and 10 for my y max. And then I get this lovely graph right here, which if you check does have at t equals 0, 2 comma 6 as the point. And if we check at 3, it does have 20 comma 9.